Welcome to today's webinar from CT to CFD Biomedical Simulation with Moving Geometries. Thank you for joining us today for the 8th installment of the 2024 CONVERGE webinar series. My name is Matthias Sulis and I am part of the business development team at Convergent Science. I will be your host for today's event. It is very exciting to be here with you today and learn from another partner of ours, Synopsys, about biomedical simulation in CONVERGE. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. The Simpleware product at Synopsys develops an industry-leading 3D image processing platform for visualization and analysis of 3D scan data and conversion into high-quality models. Simpleware software is used in the life science, clinic application, and materials and manufacturing. Easy to learn and use, the software links the latest imaging technologies to multiple design, simulation, and 3D printing application. Now it is time to introduce our speakers for today's event. Tejas Patel is a research engineer on the new application team at Convergent Science. He received his PhD in 2023 from Michigan State University, where he focused primarily on biomedical CFD application, including cryoballoon ablation for pulmonary vein isolation and EFM-based fluid structure interaction modeling of left ventricular flows. Tristan Burton is currently the director of new application at Convergent Science. He has more than 25 years of experience in CFD in a wide variety of application areas, including multi-phase flow, two-stroke engine breathing, and conjugate heat transfer. He began his career on the faculty at the U.S. Naval Academy, teaching fluid mechanics for engineering majors and thermodynamics for English major, before transitioning to engine CFD at a pair of startup companies. In 2015, Tristan joined Convergent Science as the first employee at the Convergent Science Detroit office, where he led sales and technical support effort before moving to his current role in 2019. He received his PhD in mechanical engineering in 2003 from Stanford University. Kerim Genc is a senior staff product manager for the Simpleware group at Synopsys. He has expertise in patient-specific image-based workflow for surgical planning and medical device guide design, and focuses on the product roadmap, strategic vision, partnership, and outbound marketing content development. Kerim earned his doctorate in biomedical engineering from Case Western Reserve University. During today's webinar, if you have a question for our three speakers or the rest of the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to our speakers. Kerim will go first. Thank you all.
Thank you, Matthias. Thank you for introduction. My name is Kerim Genc. I'm a product manager with the Simpleware group at Synopsys, and I wanted to talk a little bit today about the Simpleware group within Synopsys and how we've converged CFD on some image-based modeling applications. So just to give you a little bit more information about the Simpleware group, we are within Synopsys, and the Simpleware group develops high-end 3D image processing software. From a high-level overview, a simple message for you to take home today is that we go from 3D images to models. However you define 3D images and however you define models, that can vary, but it's essentially taking 3D images, converting them into models for things like measurements, or simulation, like what we're talking about here, 3D printing, medical device design, things like that. So again, 3D images to models is what we do. We have a dedicated sales, support, and services team headquartered in the United Kingdom. Synopsys, of course, is based out of California, but our particular group is our center of gravity is in Exeter in the United Kingdom, but we have a global presence within the Simpleware group, with myself being on the West Coast up here in Seattle, and then we have other team members in the US and other parts of the world. And we work with customers in clinical, life sciences, materials, manufacturing sectors, and more. And for this particular webinar, we're looking at more life sciences based, anatomically based simulation and modeling. So to give you a bit of a background of what we define in our basic area, there's three main areas. There's clinical 3D imaging, segmentation, there's a lot to unpack within that, and then simulation, which I'm sure most of you are aware of on the simulation side. So clinical 3D imaging, that's typically magnetic resonance imaging or MRI, or computed tomography or CT. So these are imaging modalities that I'm sure many people attending, myself included, have had done. So an MRI or a CT scan, which one you do depends on what type of pathology your physician wants to examine within your body. So how you can picture this is from that imaging, you get a stack of 2D images. So if you almost picture like a plane at the top of your head and then working its way down. So as you can see on the bottom left here, you have the sliced image data that you'll see. And this particular one would be from a CT scan, for example, as it slices through your head from the top to the bottom. So that image data set, that's the for Simpleware. Once you get those images, how do you extract value from those images? How do you get models? How do you do measurements? How do you, go about your workflow to enhance things you're doing? And within the medical device field, anything looking in the life sciences, wearables, anything that interacts with the human body, the design process, a lot of people have taken on simulation to enhance their design process. And on the other end is taking on more variability in anatomy, more accurate anatomical modeling to fit into those design workflows and improve your products. So in the middle here, we call it segmentation. So that's the process of going from images, extracting the anatomy of interest, and making a model out of that. So segmentation is that process of, whether it's painting pixel by pixel or using semi-automated statistical methods, or in other cases where we have AI algorithms that fully automate the process to extract those geometries. So you can see here an example of a heart from some image data, or a pelvis here. And then the last part is simulation. And that's when we get into things like CFD, mechanical, electromagnetic, different types of simulation that people run. And in this case, obviously with CONVERGE CFD, is looking at computational fluid dynamics, and that's typically done in the cardiovascular system, arteries, blood flow, fluid flow, things like that within the human body. So it's a bit of background of the space we play in, going from clinical 3D images to modeling and simulation. So Simpleware for the medical and life sciences is a 3D image-based modeling software that fits different markets. So in the gray area here, you'll see on the left side, we have the image processing. So again, this is an example of a CT scan of a patient's pelvis. You go through the segmentation process where you extract the geometries, you generate a model, you can do some analysis and reporting. This is all within the software. So again, image to model, do a little bit of analysis, and then from there you can export these models. And there's three main areas three main markets within the life sciences that we work with. So there's implants, guides, and surgical planning. So this is mostly patient-specific implants, designing these patient-specific implants. And there's a lot of companies doing this where they're using our software and our AI tools to automate this process and are doing it in production for patients as we speak. One company recently, we deployed a solution. They're doing 100 patients a day, and they're processing this data. They're taking in the CT scan, they're generating the models, they're designing the devices, and they're sending it to doctors to implant in patients, or to guide that process, or to help plan that surgery. So that's one of our main areas. Another area which is more on the R&D side of things is simulation and things like in silico trials. So in R&D simulation is, when you have R&D groups within medical device companies where they're trying to improve their designs and do virtual patients, or I guess you call it digital twins of patients, of their devices, and bringing in the anatomy into the modeling and simulation workflow to improve their design process. And then in silico trials, this is where you would leverage simulation with things like clinical trials, and to use simulation in lieu of actual patients. So you have less patients, you do more simulation and do these clinical trials faster. And then the last area is point of care 3D printing. So this is where at the hospital level, you have doctors who get these scans, and then they can extract these geometries and send them to a 3D printer, and then plan their surgeries, show their patients, say, hey, this is your heart, this is where this artery is connected incorrectly, and this is how I'm going to correct it. So that is also a growing area that we're seeing more and more within hospitals. So really, our customers consider Simpleware a best-in-class tool for medical image processing, again, CT or MRI, manual all the way to AI-enabled automated segmentation. We have a lot of customization with scripting of the GUI and our AI tools, and then export STL, 3MF CAD, or simulation exports for varied contexts of use. So really, again, that image to model workflow, and then from there, we have all the different exports you need to cover your workflow needs. So looking at a patient-specific workflow for a medical device and pharma, Simpleware can unlock the information captured within medical imaging. So again, you start from the medical image data, you go through, you do the image segmentation, generate your model, and in this case here with CONVERGE CFD software, we can develop these models. So again, we can convert the DICOM models into simulation models. We have off-the-shelf and customized AI-enabled solutions where we can fully automate these workflows. We have FDA clearance and CE marked versions for when the workflow is scaled to clinical applications. So we've got a lot of regulatory clearance covered. And then on the Converge CFD software side, medical device companies wanting to integrate human anatomy into their R&D simulation flows, and then also in silico trials, where you can reduce the time and cost for medical device development and clearance by reducing bench or animal testing and human trials. So really, for us, one unique we offer is the spectrum of automation. So really, how automated is your workflow depends on where you are in developing these workflows. So we develop these long-term relationships with our customers where they'll bring in Simpleware initially, just to process some images, get some models out, and then as they start to grow, in the case of surgical planning customers, they start getting more and more doctors involved, more and more patients, more and more cases that they're processing to plan these surgeries. Then we start integrating things like scripting to start automating some of these flows as they're doing it more and more. We have off-the-shelf AI tools, and then eventually they get to a point where they need a fully customized AI tool that can, automate their process. And this table here kind of shows where how the spectrum works. So you have on the left the number of data sets per year, say, that a customer is using, and the relative time savings. And then we have this manual to fully automated kind of spectrum. And then on the left, you see Simpleware Scan IP Medical. That's our FDA cleared version. This is the off-the-shelf tool where you'll be building up your workflow, figuring out what you want to do. If you're doing simulation, getting some models working, and just building up that workflow. And then if you start seeing success in that and you want to expand the number of patients you're processing, you can bring in scripting, and which is in Python, C#, anything you can click, you can script within the interface. This is when you're starting to get more and more patients, say, per year, 50, 150 patients per year. You start saving, it can vary widely how much time you save, 30 to 60%. And then you start getting into the area where you're getting hundreds of patients per year. And then you can get some of the off-the-shelf AI tools that we offer. And I can get into those if people have questions about those. And these are trained, fully deployable tools that we trained off of our own data sets. But then you get customers even scaling up even more. They're getting to hundreds or thousands per year. We have some customers over 10,000 a month that they're processing of image data, and they need to really automate these processes. So we work with these customers. We can train AI tools based off of their data. We have all of the IP covered to ensure that it's secure for those customers, and this is where we can save 90+% of time in terms of our customers and speeding up these workflows. So with that, one last thing to mention is that we're also very involved in academia and really pushing this area of image-based modeling. When I was doing my PhD, I was using Simpleware, and we were doing image-based simulation. Mine was more mechanical loading, musculoskeletal stuff. But really, a big investment for us has been the Simpleware University bundle. It's been about a year that we've had it available. It's 50 full research licenses, all functionalities with no technical limitations, includes all of our AI-enabled auto segmentation tools. It's floating network shared across campus, incorporated into courses, and it's a very reasonable pricing that we can get into. I'm happy to talk to people about it, and it's for peer-reviewed fundamental research. So we're really reducing the barriers and enabling people to do this. And it's about $1,500 a year for 50 licenses for academic research. So we're really pushing on the academic side to help grow this area, especially with simulation. It's still quite a bit on the academic side, R&D side, but we're starting to see more simulation being taken up into production levels within companies with simulation-based medical devices even coming up. So we're really trying to push this and enable people to do this and eliminate barriers as much as we can. And our fundamental value is definitely our AI-enabled tools, and then the quality of the models that come out and our ability to run those within simulation tools. So with that, I would like to thank you for your time and pass it on to Tristan. Thank you.
And now it is time for Tristan and his presentation. Thank you.
Good morning, everyone. How am I doing, Matthias? My volume good?
Yes, thank you, Tristan.
Wonderful. Okay, thanks, Kerim, for that, covering Synopsys software. And we'll get started now talking a little bit about how we plan to, how we use that software as part of a workflow here, where we're thinking about patients and their doctors and some sort of medical need. Here we've got a 3D printed heart that we can get into engineering analysis tools using using some medical imaging and some segmentation software to produce a CAD model of some kind. Once we've got a CAD model, we can then attempt to run simulations of flow, heat transfer, whatever the appropriate transport phenomena are, and we do this in some sort of engineering software, in this case, computational fluid dynamics software package. And then from that simulation, we can then hopefully provide information back to the doctor and the patient. It would be hemodynamic data, information on blood damage or clotting risk. This is all valuable information to the doctors. And we haven't really even scratched the surface yet of what CFD can do in this application area. We're just getting started. The doctors are asking us, what can you tell us? And so sort of where we're at currently. So the outlook is currently there's a mix, I would say. Some people are referring to CFD as color for doctors. There's some skepticism on the value of numerical methods in high-performance computing for many biomedical applications. However, we definitely see a lot of use of structural models, FEA-type models in the medical device community as part of their design process. And academia is definitely pushing computational fluid dynamics for biomedical applications currently. This is actually a case of deja vu for me. Went to a conference maybe about 20, 30 years ago. So I met in those years, and there were similar doubts about CFD for non-life science applications back then, engineering applications. But today we sort of see that CFD is used as a predictive tool for a wide variety of multiphysics applications, ranging from internal combustion engines to batteries, pumps and compressors, drones and rockets. There's a number of other applications of CFD. So now we have the FDA working with the CFD community to determine what it would take in order to accept CFD results in lieu of experimental test results for medical device approval submissions. So we're sort of moving towards more utilization of CFD in the life sciences. We've seen at some of our recent user conferences some great work on CFD with biomedical flows. This is some work that was presented by Alejandro from the University of Wisconsin, and he sort of did some comparisons of CFD to detailed experimental data, magnetic resonance velocimetry data, and PIV data, and confirmed that the CFD was accurately reproducing these flows in these sort of phantom geometries, which were meant to be representative of real patient geometries. However, at the time, he noted that CFD was not used clinically due to a couple of things. There's a lot of user input required. You got to get the geometry, and simulation runtime may be too long for practical purposes. And then, as far as the medical device regulation goes, there's some uncertainty in some of the user inputs to set up these models, which may cause problems for the acceptance of CFD data as part of a medical device submission. Now, Converge has a couple features that we think will help to mitigate some of these concerns, which we'll talk about in some of the coming slides. We also had Joseph from Penn State present a perspective on blood and turbulence and some of the impacts of turbulent flows on blood health and clotting. So this was another interesting presentation at our user conference. So a question you might be asking is, why should I consider Converge for biomedical applications? And one of the reasons is that in many biomedical applications, when you're dealing with a patient geometry, you are going to have what we would definitely classify as a complex geometry, and in many cases it may be moving. This is something that Converge is well suited for, whether it's a prescribed motion, meaning you set up the motion ahead of time, or if you want to calculate the motion as part of your engineering solution, engineering simulation. And for us, it's no more difficult to set these cases up than to set up a simple stationary geometry. Converge will build the mesh for you, and then it will figure out, using autonomous meshing technology, how to refine that mesh where it needs refinement. So we look on the left-hand side, we've got sort of a base grid that fills the space with uniform cells. In the middle panel, we sort of see some additional refinement added near boundaries, because we know there's usually a need for increased cell count there to capture the gradients. And then while the flow is being calculated on the lower right-hand panel, we see that we can add cells wherever there are, or where there's a lot of curvature in the velocity field, because we know that's an area where there'll be a large error in the solution. So this will help to improve solution accuracy for a given cell count, so that you get the best solution possible for the amount of numerical work you're willing to pay for. So here's an example based on geometry shared with us by the University of Wisconsin of an ascending and descending aorta, and you can sort of see the AMR sort of changing the changing the cell distribution as the flow sort of goes through its regular cyclical motion. And we're picking up the reductions in velocity magnitude near the walls due to the no-slip condition there. You can sort of see the velocity magnitude as it sort of makes its way down on the outer edge of the descending aorta. So we have participated in a couple of conferences where we've demonstrated the utility of CFD for some medical device type simulations. This was the FDA blood pump benchmark case that you may be familiar with. We've also seen Penn State do some validation work of their own with their own pump to confirm that CFD was producing an accurate picture for a prescribed moving geometry. Meaning you set the motion up ahead of time and you sort of tell it where to move. We're also doing a lot of work recently with heart valves, and these are sort of responding to the application of pressure and shear forces from the surrounding fluid. And we've done a number of these with both rigid body FSI motion, talking about a mechanical valve with a leaflet that maybe just you see on the right here, sort of flipping open and closed. And then we might have a more of a biological valve motion, where there's a lot more going on the structural side. We've got a deformable FSI, and we need some contact models to allow the leaflets to sort of close against each other. And so this is something that we may rely on imaging to try and get pictures of, or we've got geometry from a medical device manufacturer. We've done some of those simulations as well. All right, so this is sort of a hot area. People are asking us, how do I use your tool to make a submission to the FDA? So you may have seen the verification and validation standard that was put together by the FDA and the ASME. And they also provided a sequence of test cases that could be used to validate CFD codes. And one was a centrifugal blood pump we saw on the previous slides, and one was a nozzle. And the interesting thing about the nozzle is that they picked a range of flow regimes that were quite challenging for not only the CFD, but also the experiment. So that transition regime that we see there, at the Reynolds number of 2000, is difficult because it sort of will switch back and forth between a laminar flow and a partially turbulent flow. That can make it difficult to get consistency between experimental data and also CFD data. The FDA likes to see or wants to see that the influence of your modeling would not lead to a disastrous consequence. That's sort of the summary of this slide. The model is only a small influence in sort of the conclusions that you reach for your device, and a wrong decision does not lead to a very dangerous result for the patient, and that's probably going to be much more acceptable. See in the lower left-hand corner there of the diagram, there's something up in the right-hand corner where the model is the main thing allowing you to make a conclusion, and it may result in immediate danger to the patient. So as part of this risk assessment, the FDA is asking that the results that are submitted have some established credibility. They want to know that the software quality assurance practices that were followed by the code provider were sort of adequate. And they also want to know that the code has been verified to make sure that it gets the right answer. And they've got a level of credibility here in the numerical code validation ranging from A to D, where A is sort of you didn't provide any numerical code validation data at all, and D, you went all the way to figure out what the order of accuracies of that code. So this is something that we've been asked about for some simple test case type flows. So we'll talk about that for a little bit here. If you want to specify your order of accuracy, you need to have a solution to compare to, either an analytical solution or even your solution run on a very fine mesh to reduce the error associated with meshing. And you then sort of run a sequence of mesh calculations to confirm that the error does what you expect it to. So for those of you who are CFD experts, you'll be familiar with these terms. We convert our equations to a set of algebraic equations that we can solve on a computer by using numerical differencing stencils. And those stencils sort of provide different orders of accuracy. So a first or second order accurate stencil means that the error will drop by a factor of 2 or 4 as you cut the grid size by a factor of 2. And what we see a lot in a lot of commercial codes and even a lot of academic codes is there's a mix of first and second order differencing, because first order differencing provides stability, the second order differencing provides accuracy, and you sometimes need a little bit of both. The challenge here is that for real geometries, to set up a sequence of sort of steadily refined grids may be a challenge, because the geometries are complex and building those meshes may be hard. Converge, of course, makes that easy because you just have to refine your base mesh and you get your uniform reduction in grid size. But there's some caution advised in interpreting these results when you're trying to determine your numerical order of accuracy. These are the volume-weighted velocity errors from a one-dimensional flow, which is basically a pulsing pipe flow. What we see is that for the 1 millimeter grid in the circles and the 0.5 millimeter grid, we see a substantial drop in the error as we refine the grid, which is good. I've got here triangles on there to indicate first and second order. You see that the results are somewhere in between first and second order, but this is not just a result of the differencing we use. We actually use all second order differencing. It's also a result of the error terms themselves. For this particular velocity profile, it's only a radial profile, and we're solving in a coordinate system that's Cartesian, so that produces some complications in terms of providing a uniform grid reduction in the direction that the truncation errors are important. So some caution is advised when using simple test cases for establishing the order of accuracy. You may want to use a more complex case that's not going to have some sort of coordinate system impact. All right, so that's the end of my part. I'll now pass it over to Tejas for the next part.
Thank you, Tristan. We're going to now proceed with the demonstration from Tejas.
Thank you, Tristan, for that description about detailed description of Converge. Now I believe we have a better understanding of both the softwares, Simpleware and Converge. So I'm going to give a description of the workflow in first segmenting biomedical CT scan in Synopsys, which is the Simpleware software, and then exporting an STL file and running CFD on it in Converge. Started in Simpleware. So one thing that I've realized using in my experience in using Simpleware Medical is that it has been very easy to extract or segment geometries for biomedical CFD in general. And Simpleware also allows you to create tetrahedral meshes CFD to run CFD for any segmented geometry over a wide range of mesh output formats. Besides that, Simpleware also has some auto segmentation tools that will readily help you segment cardiac CTs, cardiac CT scans. So this is how the Simpleware window looks like. Today we are going to work on one of the tutorial guides in Simpleware software, which is the arterial blood flow. So let me go ahead and load up the CT geometry for the tutorial. So yeah, there you go. So yeah, so we have the coronal, axial, and the sagittal radiographic views over here. And at the top, we have the image processing, surface tools, volumetric mesh tools, and the 3D printing tabs. These three views are basically just the front, side, and the top views in the radiographic terminologies. So let's go ahead and begin with the workflow. So to start with, we can do the image processing and run the threshold tool, which is mainly just to extract the grayscales from the CT scan from a lower to a higher threshold. So I'm gonna go ahead and hit apply. That creates a first mask for me, and to visualize that, that's how it looks like in 3D. This gives you a better idea of that. So here you can see that we still need to clean up a lot of the geometry, and we have a lot of unnecessary small arteries that are not needed for CFD. So to go ahead and do that, I'm going to use the mask flood fill tool and hit it on the main geometry. So that creates a new mask for me. Let's say if I go ahead and visualize that, you can see that it has already cleaned most of the 3D geometry. So the next thing that we can in the workflow to go ahead with is we also still do not need these top sections or the small blood vessels that we have up over here. So this can be removed by just using a simple cropping tool in image processing. So you can go ahead and just crop the top part of it. So I'm also gonna go ahead and crop a little bit of the front side of the ascending aorta, just because I have a smoother and a flatter surface up over here. And then the same with the descending aorta at the bottom side over here. And I hit apply. So there you go. Yeah, that's better. So yeah, this is the cropping tool that we applied on the mask 2, cropping operation that we applied on the mask 2. Now to go ahead with, we still need to remove these small, so here we are mainly left with the ascending descending aorta, the two carotid arteries, which is the left and the right, and the two left and the right subclavian arteries. But besides that, you can see that we have small branches, and we still need some cleaning to be done before we can run CFD on that. So we can just use some quick 3D editing tools over here. In image processing, we can use simple 3D editing. We basically need to, let's say, for example, move this segment over here. So we can use like a lasso, delete frustrum. And all I need to do is just kind of cut this branch out so that I can later apply a mask flood fill tool on that, and so on and so forth. I do it for all these other small branches as well. And then I have this major chunk on the left subclavian artery that I need to remove. Yep, looks like we are almost good to go. Maybe have one more branch over here. That's better. And then we have a few few others on this side. So after this cleaning operation, we can again apply the mask flood fill tool on this mask too, and select the main branch. So now if I visualize the mask 3 which was just generated, you can see that it's more cleaner. It's a very clean geometry as compared to the previous one. And then once we have this, we can go ahead with applying a smoothing filter, a recursive Gaussian type of smoothing filter with a default pixel value of 1.6. And then let's say if I visualize this, you can see that it has already smoothed the geometry. And now this seems ready to be run, to import it into Converge and run CFD on. So here we have the ascending aorta as the inlet. At the bottom, we have the descending aorta outlet, and we have two left subclavian. And we have the left and the right subclavian artery and the left and the right carotid arteries. Before we proceed, we have one more important operation to perform, which is, let's say, now we need to create a CFD model for this segmentation. So we can go ahead and drag and drop mask 3 to the CFD model, and then try to generate a volumetric 3D mesh for the same. So here, let's say, like I was saying, Simpleware has options where you can export all different formats of tetrahedral meshes. So let's say if I pick VTK, and then I have a slider over here all the way from -50 to +50, which is going to dictate the resolution of the STL triangulation that is going to be generated. -50 being the coarsest and the +50 being the finest. So let's say if I pick something around like -5, that's how much fine I want my STL triangles to be. And then they also have a very important feature, which is manage and add clipping planes. So this feature kind of helps me to create clipping planes at the inlet and the outlet, which is going to be exactly perpendicular to the blood flow, to the direction of the blood flow at the outlet and the inlets. So I can drag and drop where I want to end, uh, or where I want to rather create the outlet for the CFD geometry. So here you can see it has created 5 different planes for the same. So let's say if I go ahead and export all these boundaries that I need for the STL triangulation. And now I can go ahead and generate a full volumetric mesh for that. So there you go. It already created the planes at the outlet and the inlet boundaries, and you can see how fine the STL triangulation is, it is smooth enough so that we can now import it in Converge and run CFD on this. So all I need to do next is to go ahead and export the mesh. So I go ahead and export both a VTK format, and it will also ask me for an STL export. So I'm going to go ahead and hit export, which is what we are going to use in Converge. Okay, so once we export the STL file from Simpleware, here I have imported it into Converge. You can see the STL triangulation over here. I'm just going to fade the edges so that you have a better picture. There you go. We have one inlet at the ascending aorta end, one outlet at the descending aorta, and then 2 carotid arteries and 2 subclavian arteries. So the good thing about running a CFD simulation in Converge is that we have automatic mesh generation capabilities, or AMR, which is basically adaptive mesh refinement, that will add mesh cells dynamically during runtime. This will help you improve the accuracy and improve your computational efficiency and add mesh cells only where it's actually required, based on the second gradient of the specific variable that you choose. So here's how the Converge window looks like. And to begin with, we have the case setup on the right hand side. For the user needs to set up all these tabs up over here, which is the materials. In our case, we are running a liquid simulation. The other things are all set up by default. And for the physical models, we are going to run an FSI membrane, thin membrane type of simulation. So we have fluid structure interaction enabled. So to quickly go through all these tabs one by one, for the liquid, we have blood. We have selected blood, for which the properties are very similar to that of water, with a density of 1060 kgs per meter cube. And we are treating blood as Newtonian right now. For the simulation parameters, we have the run parameters. For this case setup, we are using the compressible liquid flow solver. And the other, we are running it for 8 cardiac cycles over here. The other settings in simulation time parameters are those for the minimum time step, the maximum time step, the CFL values, and the DT move values. For the solver parameters, we have the solver settings. We can either pick between a pressure-based or a density-based Navier-Stokes solver, and then we can also set convective flux schemes for the momentum, energy, or turbulence equations if we are solving for turbulence. The next step that comes for any CFD setup is the boundary conditions and the initial conditions. So for the boundaries, we have 7 different boundaries, 1 inlet, 5 different outlets, and 1 FSI wall. So at the wall, we have no slip, but the wall motion type is FSI enabled, through which our FSI fluid membrane, fluid structure interaction membrane model functions. And then at the inlet, we have a mass flow inlet boundary condition based on patient specific mass flow data at the inlet, which is the magenta boundary over here. And then at the outlet, at all the 5 different outlets, which is the other arteries and the descending aorta, we have a Windcastle type, specifically a 3-element Windcastle type boundary conditions, which has 2 resistance, the proximal and the distance, and 1 capacitance value. So what exactly is a Windcastle boundary condition? A Windcastle model is mainly just a lumped parameter model, which is analogous to an electrical circuit. And it's essential to incorporate such a boundary condition at the outlet to account for the reaction of downstream or distal vascular elements to the subsequent potential changes in the blood flow and pressure changes downstream of the aorta and the other channels and the other blood vessels. So for the initial conditions, we are setting up velocity of 0 and a pressure of 1.18 bar in the entire domain. And for the fluid structure interaction model, like I said, we have a thin membrane model with a uniform thickness currently of 1 millimeters and a density very close to that of blood, which is 1090. And because the density of both the membrane and the blood is very similar, we have an implicit FSI model enabled. Like I said before, in Converge, we don't really need a tetrahedral mesh to begin with. We can just import STL files, and Converge dynamically generates the mesh for you during runtime. But even to do that, we still need to provide some grid control strategies, which is mainly to begin with the base grid, the AMR, and in my case, I also have the fixed embedding enabled. The base grid is basically just a Cartesian grid in the X, Y, and Z direction. With, in my case, I have a base grid setting of 2 millimeters in either directions. So like I mentioned, for the adaptive mesh refinement, I can pick any variable that I prefer to add mesh cells with. In my case, I'm choosing velocity, but here I can go ahead and add temperature, pressure, density, anything. And then I need to specify the level of embedding for that. For fixed embedding, I'm providing a boundary type of fixed embedding, which is kind of adding a fine mesh layer at the boundaries. And in my case, all the 7 boundaries, and my level of embedding is 1. So ideally, what's going to happen is my grid size at the boundaries is going to be 1 mm. And then at the last, we have some output and post-processing tabs where we can specify 3D output files for pressure, temperature, velocity, or wall displacement, wall stresses, to visualize it in either TechPlot or ParaView. And then we also have some output text file settings, which is going to dictate the frequency of writing the text files for your quantitative parameters like mass flow and pressure at the outlet or at the inlet. So yeah, that's how easy it is to actually just set up the case setup in Converge. And once you have that ready, all you need to do is you need to export the input files to one of the directories, and you can just run it using Converge 4.0. So that's how streamlined it is to first segment geometry, a segment CT scan in Simpleware, extract an STL file, import it in Converge, and then after you set it up in Converge, just export the import files and run it. So here I have a quick recap or a summary of the Converge case setup that I just presented. We are running it in Converge 4.0 with the liquid compressible solver, considering blood as a Newtonian fluid. We have a base grid of 2 millimeter in either direction. I've specified again the boundary conditions and the initial conditions as well. Over here, you can see the inlet mass flow boundary condition at the magenta inlet. And this is the 3-element Went-Castle boundary condition at the outlets that I was talking about before. And now taking a closer look at the results, here I have some profiles for the wall displacement, the pressure, and the velocity profiles for over 3 cardiac cycles presented. You can see I have scaled the wall displacement by a factor of 4, but you can see how the pressure and the velocity is varying inside the aorta and the other vessels. So here are some other graphs and output graphs from the simulation. I have compared my current membrane model results with another case setup which has just the rigid walls as well. So you can see that the mass flow rate in the subclavian and the carotid arteries for the membrane model is a little bit less than the rigid case. This is mainly due to the compliance of the arteries. And you can see the percentage change in the volume of the entire STL geometry at the bottom left over here. You can see that it varies up to 110% to about like 90% over 3 cardiac cycles here.
All right, thank you for all the speakers. It was a very interesting presentation. You can see here on your screen on two QR codes. The one on the left, it's about news at event. This would be kind of to register to our mailing list and for you to get the latest news in relation to Converge, in relation to any future events or any development with the software. The QR code on the right will take us to the contact us page. So if you have any question about the software licensing, please reach out to us and we will be happy to share more information with you. The last slide is about our 2024 Converge webinar schedule and archive. You can scan this QR code and access the section of our website with our future events for this webinar series, as well as accessing the link to past event and view them for all the other application and all the other events that we hosted. Thank you again for attending today and for your question. Have a great rest of your day.